We now jumped to interference and how it affects the system capacity. And we see now that the interference is a major limiting factor in the performance of cellular radio systems. And some sources of interference include another mobile in the same cell, a call in progress in another cell, other base stations operating in the same frequency band, or any non-cellular system which inadvertently leaks energy into the frequency band. So those are the major causes of interference, and I think we have properly articulated them. And then we classify the interference on voice channels as causing crosstalk. And in that case, the subscriber hears interference in the background due to some other undesired transmission. On the other hand, when the interference permeates the control channels, and you remember that control channels are responsible for setting up the calls or allocating channels to, or allocating voice channels to the requester, then those control channels are going to malfunction in the presence of interference, and this will lead to missed and blocked calls due to the errors in digital signaling. So finally, interference is more severe in urban areas, and of course that is where there are most electronic devices, and electronic devices, be Wi-Fi or microwaves, are likely to cause greater noise than in the rural areas. And therefore, even there are plenty of there's a huge number of base stations, and you remember that the base stations are transmitters or transceivers, and even the number of mobiles are also very many, and therefore there is likelihood that some of the mobile devices might leak some energy into the channel that a user is using, and therefore this would cause some interference. And therefore we see now that interference has been recognized as a major bottleneck in increasing capacity and is often responsible for dropped calls. And we say now that the two major types of system-generated cellular interference are co-channel interference and adjacent channel interference. And that we already mentioned in the previous lecture, and therefore we are going to look at each one of them. We're going to start with the co-channel interference and see how it affects the system capacity. So remember that we say the co-channel interference is the interference due to two cells that are using the same set of frequencies. So there is cell, this is my hexagonal cell using frequencies that we have grouped as A, and then at some other distance, we classified the distance between two cells as D. So another cell some distance apart from the previous cell that is using the same set of frequencies. So these two cells, these are the ones that are cause the interference due to using the same set of frequencies. So as long as when the D becomes small, then the interference I is likely to increase unless we have reduced the power of the transmitter base station at A1 and A2. But still, we are saying that there is likelihood of some interference, and that interference is the one that we are referring to as the co-channel interference. So unlike the thermal noise, which can be overcome by increasing the signal-to-noise ratio, or SNR, we cannot be able to overcome the challenges of co-channel interference by increasing the transmitter power. In fact, we normally try to overcome the co-channel interference by reducing the power of the transmitter. This is because an increase in the carrier transmit power increases the interference to the co-channel neighboring cells or neighboring co-channel cells. So if you increase the transmit power of this one, then it is likely to leak and almost reach these other co-channel cells. And therefore, to reduce the co-channel interference, co-channel cells must be physically separated by a minimum distance to provide sufficient isolation due to propagation. So we normally say that between A and A1 and A2 here, you must have some minimum distance D minimum, so that we are providing sufficient isolation to mitigate or to combat the cochonal interference. When the size of each cell is approximately the same and the base station transmits the same power, cochonal interference ratio is independent. So remember we defined some ratio that comes from the frequency reuse factor. Remember that? Frequency reuse factor. And therefore, we are saying now that when we have the same size of the cell and the transmit power remains the same, this ratio is independent of the transmit power and becomes a function only of the radius of the cell. And we will see that shortly. And the distance between the two centers of the Cochano's cells or the nearest Cochano cells. So you're saying that, as we are saying, if the radius of this cell 1 is r, and the radius of this L2 is r, and the distance between the two, then we say that this Cochano ratio, that sometimes we denote as capital Q, actually, capital Q is normally given by D over R, where D is the distance of separation of the two Cochano cells, and R is the radius. So the bigger the D, the bigger the ratio. And this ratio simply says that the bigger it is, the lesser the interference you're likely to have. So by increasing the spatial separation, which is the ratio of D over R, sorry, by increasing the D over R, the spatial separation between Cochano cells relative to the coverage distance of the cell is increased, and thus the interference is reduced from the improved isolation. So this factor Q is an indicator of how much cells are isolated or how much Cochano cells are isolated from one another. And therefore, you're saying the parameter Q, which is also called Cochano reuse ratio, is related to the cluster size. I will show that shortly. So if you recall that we had expressed the ratio of, that we had said that the distance between two cells D, two cell centers D was given by this formula, that is D is equals to root 3 NR. Then since we are saying that the cochonal use ratio is given by D over R, we might find that this is equivalent to saying that this is root 3 N times R divided by R, and therefore we can simply cancel out that R, and you are left with root 3N. And therefore, what we will find out is that N, of course, is always the number of the cells in a cluster, or what we refer to as cluster size. And for that reason, therefore, we are able to find the cochonal use ratio Q for any given size of a cluster. For instance, when N is 3, we find that the cochonal use ratio is 3 times 3 becomes, and then root 3 times 3 becomes 3. Similarly, when we find the cochonal use ratio Q for N is equals to 7, it is simply a matter of saying that it is root of 7 times 3 becomes 21. Root of 21 gives you 4.58. That is very important because we will see how it affects the capacity of, or the interference that a certain cell in a cluster is likely to experience. So the higher the reuse ratio, as we are saying the lesser the interference that the cells or the Cochano cells are going to experience. Now, if we let I naught to be the number of Cochano cells, and we have said that for hexagonal geometry, we are saying that this is a cell. One cell is neighbored by 6 other neighbors, and therefore at some distance D from this cell to another cell that is using the same set of frequencies, there of course, this cell is causing or likely to cause some interference, and that is, we call that other cell Cochano interfering cell in tier 1. I think we have also discussed the concept of tier 1 at some other lecture. So we're saying that one side is going to experience one cell, another side is going to have another cell that is Cochano. So there are actually 6 of them, or what we are saying I for hexagonal is going to be equals to 6 for the first tier. So we say that let I not be the number of Cochano cells. At a point, I just think that I'm going ahead of myself by saying that for hexagonal geometry, I is going to be 6. Then the signal to noise ratio, the signal to interference ratio, SI, is for a mobile receiver which monitors a forward channel may be expressed as follows. We simply say that the signal is I, but it is going receiving interference from I number of Cochano cells. So of course the number of Cochano cells is going to be equals to 1 all the way to I naught. So we are saying that at some point this value for hexagonal geometry, this is going to give you a 6. So why are you saying that of course the S is the desired signal power from the desired base station, and I, this is the power, I is the power or the interference power or the power of that base station in the interfering cell. So you're saying that of course this is the interference power, and it is caused by the ith Cochano interfering cell or base station. So by following propagation measurements in a mobile radio channel, we can show that the average received signal strength at any point decays as the distance of the separation between the transmitter and receiver, and this follows the typical. At a point, we might use the Fries propagation model. You may go with that if you are not conversant with it, but it is the basic propagation model that tells you how power decays as you go away from the transmitter. It is called power law, and we can say that this received power may be expressed as a fraction of transmitted power multiplied by the ratio of the distance from the distance d divided by d naught, where d naught is the cruising reference point in the far field region of the antenna at a small distance d naught. D naught is that small distance that we may count. We have a reference antenna at a distance d naught from the BTS. So this is what we are referring to as the d naught, whereas now the d is the distance d of the mobile receiver. So we normally compare the power that would be received by as a reference antenna here, which is a distance d naught away from the BTS, whereas now d is the distance that we are considering. So we normally take the reference antenna as to be at a cross ridge, a small distance from the BTS. And of course, when we break this formula to be expressed as in terms of decibels, then you definitely know that we change the division to become a minus, and we normally say 10 log of power. So if it is log of PR is equals to 10 log of P naught, and with d over d naught power minus n. If you just express this one, this now becomes PR expressed in dBm or dB milli, and this is going to be equals to again P naught dB milli. These are the expressions of decibel meter or milli. This is actually what we define as decibel milli. It is an expression of decibel in milliwatts. Then, of course, when you say this is times 10, this will become minus 10 n log of d over d naught, and that simply solves this equation 9. We have said that P naught is the power received at a close reference point in the region of the antenna at a small distance d naught from the transmitting antenna, and then n is the path loss exponent, typically that ranges between 2 and 4 for urban cellular systems. This figure is determined from the propagation models, and we don't have to get worried how we are coming up with a 4. We might be told, assume that the path loss exponent n is going to be equal to 2, is going to be equal to 3, or equals to another number. But it is known to be ranging between 2 to 4. Now, when we consider a forward link where the desired signal is having a base station, and where the interference is due to the Cochano base stations that are some distance di apart, then the received power at a given mobile within the cell due to the interfering cell will be proportional to di naught. or di with power to power minus n. N we have already said what it is. So we are saying that we may be able to estimate or to approximate the signal to interference ratio we are talking about here. This is BTS of radius r, and therefore the user is at distance r, and he is also experiencing some interference from other di, from other, let's say I'm assuming the other di, or this is ith interferer. So this guy is going to experience some interference from that, is going to interference from that, and from that based co-channel PTS. So in few words, this device or this mobile station at this point is going to receive the power from this, and also some interference from other transmitting BTSs that are co-channel to the current cell that the user is in. In that case, we are saying that we can be able to approximate that we have already seen that when we keep the radius of the cells the same, we have seen that the ratio of interference, or the Q that we called channel use ratio, was given by D over R. And since we are saying that when this use ratio increases, the interference ratio decreases, then in a similar manner we can be able to express it. The derivation of this equation is not there yet. We are not yet doing it, but we are simply saying that the signal to interference ratio is indirectly related to this ratio. Therefore, because you can see clearly that this is D over R, but we have also seen that the signal to interference ratio is related to the power law that is derived from the Freeze propagation model. Then we can say that if we introduce to power minus n here, and then take the reciprocal of it, it will give us the signal to interference ratio that is experienced by a mobile radio that is at distance r and at distance d from the interfering cells. So we are simply now saying that the signal to interference ratio due to I number of interference may be expressed as equation 10, and that is a very important equation. Now, if we consider only the first layer, we have talked about tires, and the first layer, and I think I demonstrated that concept of tires in an earlier lecture. The first tire is the first, if we have, this is our cell, and then the first 6 that are closest to this cell at distance D are the one that we refer to as the first tire. So they're going to be first 6 for hexagonal geometry. So when you consider the first layer of the interfering cells, if all the interfering base stations are equidistant from the desired base station, and if the distance is equal to the distance D between the call centers, then we might transform equation 10 that we have just seen up here, because we are saying that these distances are similar, and therefore when they are similar, this will be equivalent to sum of I multiplied by D. And if that be the case, then you can simply say that S over I is equivalent to R over D or over I, and to power minus n. And therefore, if you just change this reciprocal, you are going to find D over R power n divided by I. And this is what we have in equation 11. But you already know this ratio. We already found this ratio to be equivalent to Q, and we found Q to be equivalent to root of 3n, and therefore that is how we are coming up with equation 311. And we say now that equation 11 relates the signal to interference ratio to the cluster size, which in turn determines the overall capacity of the system that we define in equation 2. If you remember, equation 2 is right here. We say that the capacity is given by the number of times m that a cluster is repeated, and S is the capacity that is defined by, that is already allocated, or the number of available channels that have already been given to the mobile network operator. So we are saying that we can relate equation 11 to that equation number 2. So if we assume that the closest cells in the hexagonal geometry are going to be 6, as I mentioned, and we assume that they are close enough to create significant interference, and they are approximately equal distance from the desired base station, then we may use the US AMPS cellular system, which uses FM and 30 kilohertz channels. And we are saying that subjective tests would indicate that sufficient voice quality is provided when signal to interference ratio is greater than or equal to 18 of dB. If you use equation 11, we can show that in order to meet this requirement, the cluster size should be at least 6.49. And of course, we already saw that if we want to find S over I is equals to 18 dB minimum, then we need the ratio that we have expressed from equation 11 that says that D over R power N over I should be bigger than or equals to 18 dB. We can convert this one to become the real values without the dB format. Then we know that we get 10 SI, 10 log SI is equals to 18 dB. And therefore, we want to find SI, and we can be able to say that it is equals to 10 to power 18 divided by 10 from your calculus. This becomes 63.0, actually 0.1. And since we know I to be equals to 6, we can say that 63.1 times 6 would be equals to D would be less than or equals to D, okay, root 3n. Remember that this ratio was still given by root 3n, and therefore we'd say that this would be equivalent to root 3n to power n. When we take n to be equals to 4, then you'd say fourth root of that and fourth root of that. You're saying n is equals to 4 here, so this would cancel out. When we do that, very quick mathematics, we bring it down here. Fourth root of this value becomes 2.82, 63.1 times 6 square root divided by 3. Yes, divided by 3. Correct. It becomes, I think I just missed in mathematics, so becomes n is greater than or equals to 6.49. I think at this point I should have pressed the 18 dB at that point, because we are saying that this value should be bigger than or equals to 18 dB. So clearly the here is the greater than sign. So that is how we obtain that value, and we have even gone to the level of deriving, which was not necessarily important. So we are saying therefore that because n is not a arbitrary number, it is guided by the formula. We said that I squared plus j squared plus ij square root. Then we are saying that the biggest number bigger, okay, the next big number after 6.49 is 7. That is how we obtain this value. So we are saying that the minimum cluster size of 7 is required to meet the SI requirement of 18 dB. And it should be noted that the equation 11 is based on hexagonal cell geometry, where all the interfering cells are equidistant from the base station receiver, and hence provides optimistic results in many cases.